Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The Feynman Lectures on Physics, a monumental three-volume compendium published in 1964, stands as a distinct achievement in physics education, conceived initially as a means to invigorate the California Institute of Technology's introductory physics curriculum. The lectures, delivered by Richard Feynman with contributions from Murray Gell-Mann, James Hartle, and John Wheeler, transcend the limitations of a conventional textbook. They offer instead a profound exploration of fundamental physics principles, characterized by Feynman's unique pedagogical approach, emphasis on conceptual understanding, and relentless pursuit of clarity. This essay undertakes a systematic examination of the core claims, arguments, and methodological approaches espoused within the Feynman lectures, critically evaluating their strengths, limitations, and lasting impact on the landscape of physics education. Section 1, Introduction to Mechanics and the Concept of Energy. The initial lectures, constituting the first volume, establish the groundwork for mechanics by introducing fundamental concepts such as motion, force, and energy. Feynman commences with a discussion of space, time, and motion, establishing a framework for describing the physical world quantitatively. He emphasizes the importance of precise definitions and the role of mathematics as a language for expressing physical laws. A central argument presented is the concept of energy conservation, positing that energy cannot be created or destroyed, only transformed from one form to another. Feynman illustrates this principle through various examples, including the motion of a simple pendulum and the collision of billiard balls. His approach avoids sophisticated mathematical formalism, instead favoring intuitive explanations and physical reasoning. One noteworthy aspect of this section is Feynman's introduction of the principle of least action, which states that a physical system will evolve along a path that minimizes the action, a quantity related to the energy of the system. While initially presented as a curiosity, Feynman foreshadows its profound implications, particularly in the context of quantum mechanics. It is worth noting that the treatment within these introductory lectures may not fully satisfy those seeking immediate mathematical rigor. Feynman prioritizes accessibility and conceptual comprehension, setting the stage for a more mathematically intensive exploration in subsequent chapters. Section 2, Newtonian Mechanics and the Law of Gravitation. Building upon the foundational concepts, Feynman delves into Newtonian mechanics, elaborating on Newton's laws of motion and the universal law of gravitation. He meticulously explains the concepts of inertia, force, and momentum, demonstrating how these principles can be used to predict the motion of objects. A key claim within this section is the universality of the law of gravitation, asserting that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Feynman provides compelling evidence for this claim, referencing astronomical observations and experiments, such as Cavendish's measurement of the gravitational constant. The lectures also rigorously explore the concepts of potential energy and work, demonstrating their relationship to force and motion. Feynman's exposition of these concepts relies heavily on geometric reasoning and visual aids, making them accessible to students with varying mathematical backgrounds. He effectively uses examples of planetary motion and rocket trajectories to illustrate the power of Newtonian mechanics in predicting real-world phenomena. However, it is crucial to acknowledge the limitations of Newtonian mechanics when applied to extreme scenarios, such as objects moving at relativistic speeds or in strong gravitational fields, contexts that are addressed in later volumes. Section 3, Conservation Laws and Symmetry. A significant portion of the first volume is dedicated to the discussion of conservation laws and their connection to symmetry. Feynman elucidates the profound relationship between conservation of energy, conservation of momentum, and conservation of angular momentum, and various symmetries in physical laws. For example, he demonstrates that the conservation of energy is a consequence of the time translation invariance underlying physical laws. Similarly, the conservation of momentum is linked to spatial translational invariance, and the conservation of angular momentum is linked to rotational invariance. The lectures highlight the significance of Noether's theorem, which formally establishes this connection between symmetries and conservation laws. Feynman uses these concepts to analyze the motion of rigid bodies and the dynamics of collisions, providing a deeper understanding of physical phenomena. He emphasizes that these conservation laws are not merely empirical observations but rather fundamental principles that govern the behavior of the universe. The exposition on symmetries provides valuable insight, particularly in advanced physics, where invariance principles play a vital role in constructing physical theories. While Feynman presents these ideas in a simpler context, the underlying concepts remain central to modern physics. Section 4: Oscillations and Waves. The exploration of oscillations and waves marks a shift towards more complex physical phenomena. Feynman introduces the concept of simple harmonic motion and discusses its application to various physical systems, such as a mass suspended on a spring or a simple pendulum. He demonstrates how to solve the differential equation governing simple harmonic motion and explains the concepts of frequency, amplitude, and phase. Feynman then extends the discussion to waves, including transverse waves and longitudinal waves, illustrating their properties and behavior. He elaborates upon the superposition principle, explaining how waves can interfere constructively or destructively. A crucial aspect of this section is the connection between oscillations and waves, highlighting how any periodic motion can be represented as a superposition of simple harmonic oscillations. Feynman presents Fourier analysis as a powerful tool for analyzing complex waveforms and decomposing them into their constituent frequencies. He discusses the application of Fourier analysis to various fields, including acoustics and optics. Feynman's innovative approach lies in his explanation of wave phenomena through mechanical analogies, emphasizing the underlying physical principles. However, the mathematical treatment of complex wave phenomena such as diffraction and interference might require further elaboration for some Section 5: The kinetic theory of gases. The section on the kinetic theory of gases develops a statistical approach to understanding the behavior of macroscopic systems. Feynman introduces the concept of temperature as a measure of the average kinetic energy of molecules within a gas. He derives the ideal gas law, relating pressure, volume, and temperature, based on the assumption that gas molecules are point particles that undergo elastic collisions. A central claim is the equipartition theorem, stating that each degree of freedom of a molecule contributes equally to the total energy of the system. Feynman uses this theorem to calculate the specific heat capacities of various gases and explains the deviations from the ideal gas law that arise due to intermolecular forces and the finite size of molecules. He also introduces the Boltzmann distribution, which describes the probability of finding a molecule with a given energy. The Boltzmann distribution provides a powerful tool for understanding the behavior of systems in thermal equilibrium. Feynman's detailed explanation of entropy and irreversibility is noteworthy. He elucidates the second law of thermodynamics, stating that the entropy of a closed system always increases over time, and connects it to the statistical behavior of large numbers of particles. He emphasizes that while microscopic processes are reversible, macroscopic processes are often irreversible due to the overwhelming probability of increasing entropy. Section 6: Thermodynamics. The section on thermodynamics solidifies the concepts introduced in the previous section, formalizing the laws of thermodynamics. Feynman delivers an in-depth explanation of the first law of thermodynamics, affirming the conservation of energy within a thermodynamic system. He clarifies the difference between heat and work, demonstrating how these are forms of energy transfer. In his discussion of the second law, Feynman elucidates the concept of entropy and its relation to the irreversibility of processes. He provides several illustrative examples, such as heat engines and refrigerators, to demonstrate the limitations imposed by the second law on the efficiency of energy conversion. The emphasis on the statistical interpretation of entropy, linking it to the number of possible microstates corresponding to a given macrostate, is a particularly salient aspect of this portion. Furthermore, Feynman explores the concept of the Gibbs free energy and its relevance to chemical reactions and phase transitions. He emphasizes how the minimization of Gibbs free energy determines the equilibrium state of a system under constant pressure and temperature. The link between thermodynamics and statistical mechanics becomes increasingly apparent throughout these lectures, highlighting the power of statistical methods in understanding macroscopic phenomena based on microscopic interactions. Section 7: Radiation. Feynman addresses the topic of radiation, beginning with a discussion of blackbody radiation and its spectral distribution. He introduces Planck's law, which accurately describes the intensity of radiation emitted by a blackbody as a function of frequency and temperature. Feynman emphasizes the significance of Planck's constant, a fundamental constant that marks the advent of quantum mechanics. He then discusses the photoelectric effect, whereby electrons are emitted from a metal surface when exposed to light. He explains how Einstein's theory of the photoelectric effect, which postulates that light is composed of discrete packets of energy called photons, resolves the paradoxes associated with the classical wave theory of light. Feynman then examined the Compton effect, where photons scatter off electrons, resulting in a change in wavelength. The Compton effect provides further evidence for the particle nature of light. This section underscores the wave-particle duality of light, demonstrating that light exhibits both wave-like and particle-like properties. Feynman utilizes visual explanations and thought experiments to effectively convey these concepts, but a more advanced treatment of quantum electrodynamics is deferred to later volumes. Section 8, Wave Optics. The lectures then transition to a detailed discussion of wave optics, exploring phenomena such as interference, diffraction, and polarization. Feynman provides a comprehensive analysis of Young's double-slit experiment, demonstrating how the interference of light waves creates a pattern of bright and dark fringes. He introduces the concept of path difference and explains how it determines whether constructive or destructive interference occurs. Feynman then delves into the topic of diffraction, explaining how light bends around obstacles. He discusses the diffraction patterns produced by single slits, double slits, and diffraction gratings. The lectures highlight the resolving power of optical instruments, such as telescopes and microscopes, and explain how diffraction limits their ability to distinguish between closely spaced objects. Feynman provides a thorough explanation of polarization, demonstrating how light waves can be polarized in different directions. He discusses various methods of producing polarized light, including reflection, refraction, and scattering. The applications of polarization in optical devices, such as polarimeters and liquid crystal displays, are also explored. While the treatment remains primarily classical, Feynman hints at the connection between wave optics and the quantum theory of light, preparing students for a more advanced discussion of quantum optics in later sections. Section 9. The properties of materials from an atomic viewpoint. Feynman shifts the focus to the properties of materials, examining how these properties arise from the behavior of atoms and molecules. He begins with a discussion of the structure of atoms, describing the nucleus and electron configuration. He introduces the periodic table and explains how the chemical properties of elements are determined by their electron configurations. Feynman then explores the nature of chemical bonds, including ionic bonds, covalent bonds, and metallic bonds. He explains how these bonds determine the structure and properties of molecules and solids. The lectures explore the properties of solids, including their mechanical properties, electrical properties, and thermal properties. Feynman discusses the concepts of elasticity, plasticity, and fracture, explaining how these properties are related to the atomic structure of solids. He examines the behavior of semiconductors, explaining how their electrical conductivity can be controlled by doping. The thermal properties of materials, such as heat capacity and thermal conductivity, are also discussed. While the treatment of solid-state physics is introductory, it provides a valuable foundation for understanding the relationship between the microscopic structure of materials and their macroscopic properties. Section 10. The wave nature of matter. Transitioning to the realm of quantum mechanics, Feynman introduces the concept of matter waves, asserting that particles, such as electrons, can exhibit wave-like properties. He presents the evidence for matter waves, including the Davison-Germer experiment, which demonstrated the diffraction of electrons by a crystal lattice. Feynman introduces the de Broglie wavelength, which relates the momentum of a particle to its wavelength. He explains how the de Broglie wavelength can be used to predict the diffraction patterns of particles. The lectures delve into the Heisenberg uncertainty principle, stating that it is impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. Feynman explains how the uncertainty principle arises from the wave nature of matter. He emphasizes the probabilistic nature of quantum mechanics, asserting that the position and momentum of a particle are not precisely defined but rather described by probability distributions. This section provides a conceptual introduction to quantum mechanics, laying the groundwork for a more mathematically rigorous treatment in subsequent volumes. Section 11. Quantum mechanics. The exploration of quantum mechanics comprises a significant portion of the third volume, delving into the principles and mathematical formalism. Feynman elaborates on the Schrödinger equation, the central equation governing the behavior of quantum systems. He explains how to solve the Schrödinger equation for various potential energy functions, such as the harmonic oscillator and the hydrogen atom. The lectures introduce the concept of quantum states, which describe the possible states of a quantum system. He presents the superposition principle, stating that a quantum system can exist in a superposition of multiple states simultaneously. Feynman discusses the concept of quantum entanglement, where two or more particles become correlated in such a way that their fates are intertwined, regardless of the distance between them. He explores the implications of quantum entanglement for quantum computing and quantum communication. This section provides a comprehensive introduction to the principles of quantum mechanics, equipping students with the tools necessary to understand more advanced topics in physics. Section 12. The Schrödinger equation in more detail. This segment delves deeper into the Schrödinger equation, scrutinizing its applications to various physical systems. Feynman expounds on solving the equation for the hydrogen atom, deriving the energy levels and wave functions of the electron. He clarifies the concept of atomic orbitals and their role in chemical bonding. The lectures address the perturbation theory, a technique for approximating the solutions to the Schrödinger equation when the potential energy function is complex. He demonstrates how perturbation theory can be used to calculate the energy shifts caused by external fields or interactions between particles. Feynman explores the phenomenon of quantum tunneling, where a particle can pass through a potential energy barrier even if it does not have sufficient energy to overcome the barrier classically. He also illustrates the applications of quantum tunneling in various physical systems, such as alpha decay and scanning tunneling microscopy. The lectures provide a more nuanced comprehension of the Schrödinger equation and its applications in atomic and molecular physics. Section 13, Spin 1. Feynman then directs attention to the concept of spin, an intrinsic angular momentum possessed by elementary particles. He notes that spin is a purely quantum mechanical phenomenon with no classical analogue. Feynman discusses the properties of spin-on particles, such as photons and W bosons. He explains how the spin angular momentum of these particles is quantized, taking on discrete values. The lectures introduce the concept of polarization for spin-on particles, demonstrating how the polarization direction can be described by a vector. Feynman explores the interaction of spin-on particles with electromagnetic fields, such as the Zeeman effect. He also explains the role of spin in the selection rules for atomic transitions. This discussion provides insight into the properties of spin and its role in various physical phenomena. Section 14, Spin 1/2. The discussion pivots to spin-and-a-half particles, such as electrons, protons, and neutrons. Feynman elucidates that spin-and-a-half particles obey Fermi-Dirac statistics, which dictate that no two identical fermions can occupy the same quantum state. He introduces the concept of the Pauli exclusion principle, which is a consequence of Fermi-Dirac statistics. The lectures explore the mathematical representation of spin-and-a-half particles using spinors. He explains how spinors transform under rotations and Lorentz transformations. Feynman also discusses the concept of magnetic moment associated with spin-and-a-half particles, explaining how this magnetic moment interacts with magnetic fields. He delves into the Stern-Gerlach experiment, which provided experimental evidence for the quantization of spin angular momentum. Section 15. The dependence of amplitudes on time. Feynman explores the connection between quantum mechanical amplitudes and time evolution. He re-emphasizes the concept of superposition, where a quantum system can exist in a combination of multiple states simultaneously. He explains that the amplitudes associated with these states evolve in time according to the time-dependent Schrödinger equation. Feynman introduces the concept of stationary states, which are quantum states whose amplitudes do not change over time. He explains that the energy of a stationary state is constant. The lectures explore the relationship between the energy of a quantum state and its frequency. He mentions the Heisenberg energy-time uncertainty principle, stating that the uncertainty in the energy of a quantum state is inversely proportional to the time interval over which the state is observed. Section 16, the Hamiltonian matrix. This section provides a detailed examination of the Hamiltonian matrix, a mathematical representation of the total energy of a quantum system. Feynman explains how the Hamiltonian matrix can be used to calculate the energy levels and wave functions of a quantum system. The lecture introduces the concept of diagonalization, a mathematical technique for finding the eigenvalues and eigenvectors of the Hamiltonian matrix. He explains how the eigenvalues of the Hamiltonian matrix correspond to the energy levels of the system, while the eigenvectors correspond to the corresponding wave functions. Feynman explains how the Hamiltonian matrix can be used to describe the interactions between particles. He demonstrates how the interactions between particles can lead to the formation of bound states, such as atoms and molecules. Section 17, Symmetry and Conservation Laws. Feynman revisits the connection between symmetry and conservation laws within the context of quantum mechanics. He expands on the relationship between translational symmetry and momentum conservation, rotational symmetry and angular momentum conservation, and time-reversal symmetry and energy conservation. Feynman elucidates how these symmetries are described mathematically using unitary operators. He then introduces the concept of parity, which is related to the inversion symmetry of space. He reveals that parity is conserved in strong and electromagnetic interactions but is violated in weak interactions. The lectures further explores the concept of charge conjugation, which is related to the symmetry between particles and antiparticles. He points out that charge conjugation is conserved in strong and electromagnetic interactions but is violated in weak interactions. Section 18, Identical particles. Feynman discusses the unique properties of identical particles in quantum mechanics. He elucidates the distinction between bosons, which have symmetric wave functions, and fermions, which have antisymmetric wave functions. He highlights the consequences of these symmetry properties For the behavior of systems containing identical particles, Feynman discusses the Bose-Einstein condensation, a phenomenon where a large number of bosons occupy the same quantum state at low temperatures. He also examines the Fermi energy, which is the highest energy level occupied by fermions at zero temperature. Examples include the behavior of electrons in metals and the properties of nuclear matter. Section 19 Conclusion. The Feynman lectures on physics stand as a testament to the power of clear, intuitive explanations in conveying complex scientific concepts. Richard Feynman's unique pedagogical approach, characterized by a relentless pursuit of clarity and a focus on conceptual understanding, remains deeply influential. While the lectures might occasionally lack the mathematical rigor preferred by some advanced students and researchers, their emphasis on physical reasoning and accessible explanations makes them a valuable resource for a broad audience. The detailed examination of mechanics, electromagnetism, and quantum mechanics, interwoven with insightful discussions of thermodynamics, wave phenomena, and the properties of materials, provides a comprehensive overview of fundamental physics principles. The ongoing availability and continued relevance of these lectures underscore their enduring significance as a cornerstone of physics education. Furthermore, the work embodies a unique synthesis of ideas from luminaries such as Gell-Mann, James Hartle, and John Wheeler, reflecting a synergistic intellectual environment at Caltech. The legacy of the Feynman lectures on physics extends beyond its immediate pedagogical impact, inspiring generations of students and researchers to approach physics with curiosity, creativity, and a deep appreciation for the fundamental laws that govern the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.